The ideal brilliant cut and illumination contrast. The moment you see the ideal brilliant, you understand why we care. In this video, we are diving into the optics of pure dazzle. Our subject is the round brilliant cut in both diamonds, and in other gemstones with different refractive indices. The round brilliant is that specific arrangement of facets that's been the benchmark of diamond beauty for over a century. It's revered for its brilliance, its fire, and that incredible sparkle we call scintillation. For decades, diamond cutters and gem facetors were designing and working by cut-and-try experimentation. They had found empirically that only a very narrow range of angle combinations worked best, specifically for diamond around 34 degrees for the crown and 41 degrees for the pavilion. For diamond, these angles were found through trial and error by giants in diamond cutting, first by Henry Morse back in the 1860s, and later in 1919 codified through the math of Marcel Talkowski. Edward J. Sukop and others reported on the best angles found for other gemstones with different refractive indices. For the longest time, these experts knew what worked best for each gem variety, but an adequate explanation was lacking in why those narrow ranges were best. That is exactly what is being addressed here, bridging a century of hands-on cutting wisdom with contemporary optical science through the framework of illumination contrast and the gem's spectral reflection pattern. Let's set the stage a bit. When we talk about the round brilliant cut, there are 7 parameters defining it. The 7 key parameters are the pavilion main angle, crown main angle, table size, pavilion half or lower girdle facet length, star length, girdle size, and culet size. However, the heavy lifting for light performance and much of the larger sparkles and fire, especially in the early ideal, comes down to the 16 main facets, 8 on the pavilion and 8 on the crown. Their angles were critical and central to defining top grades such as the Gemological Institute of America's Excellent and the American Gem Society's Ideal. The other parameters, most importantly the pavilion halves, are cut in relation to the main angle combination. The early ideal of both Morse and Talkowski, although different in appearance due to larger main facets, still shares with the modern ideal the same empirically found best combination of crown and pavilion main angles. Evolution of gem cut design. It's about how those crown and pavilion main angles interact with the gem's illumination. Before we had sophisticated computers and ray tracing, these angles were found purely through trial and error. Henry Morse way back in the 1860s first found the best, what came to be known as the ideal in diamond cutting. This was a 41-degree pavilion along with a 35-degree crown. Then there's Marcel Talkowski's theoretical math work back in 1919. He proposed 40.75 degrees for the pavilion and 34.5 degrees for the crown. But here is a noteworthy point he made. Talkowski acknowledged that a small range around those exact numbers could yield equally superb results. Before about 1975, the primary goal in cutting was preventing windowing. Windowing occurs if pavilion angles are cut too shallow, specifically shallower than the gem's critical angle. Cutting below this threshold causes light entering the crown to refract out of the pavilion instead of undergoing total internal reflection. As a result, light fails to return through the crown to the observer above. Pavilion facets cut below the critical angle appear dark and lack brilliance. Rather than reflecting light from above, they create a visible window to the area beneath the stone. Avoiding windowing was long considered sufficient. However, merely trapping light inside the stone is only the bare minimum. It prevents the obvious flaw of windowing, but does not guarantee the best brilliance, fire, or scintillation. Something essential was missing. That missing piece was identified by Bruce Harding. Harding was the first to emphasize the optical impact of the observer's head obstruction on a gem's light performance. With that revelation, the whole design approach shifted. It wasn't just about capturing light and avoiding leakage. It was about avoiding angles that reflect the darkness of the viewer's head back at him. Harding said that for a facet to appear bright, the entering and exiting light ray seen by the viewer must diverge by at least 10 degrees. Divergence is the angle between the incoming path and the outgoing path to your eye. The severe obstruction resulting from less than 10-degree divergence has the entering light path too close and blocked by your head. You're essentially looking almost directly back towards the area that your head is obstructing. So, you see reflections from the relative darkness of your silhouette. Harding's charts mapped crown and pavilion angle combinations, showing dark zones where this 10-degree divergence was violated. The shaded areas indicated angle combinations of severe, brilliance-reducing head obstruction. If we look at the chart for diamond, we can see that the black dot marks the Talkowski-derived optimum main angle combination of a 34.5-degree crown and a 40.75-degree pavilion. Notice this location is just outside the boundary of severe head obstruction. Harding's logic suggested aiming for angles well within the bright zones, away from the 10-degree boundary. When Harding plotted empirically validated best angles, the Morse and Talkowski angles for diamond, and those recommended by Sukop for other gemstones, the angles that history had already proven optimal. They did not fall in the middle of the bright zones away from the 10-degree divergence line. Instead, they consistently landed just outside the edge of those dark under 10-degree divergence zones. They hug the border. They do not run away from it. This appears counterintuitive. If the dark zone means less brilliance, why would the absolute best cuts flirt with that boundary? Why sit right on the edge? It seems risky. Yet this observation points to a deeper understanding and refines Harding's initial insight. The goal is not to avoid the darkness created by the observer's head. The goal is to use it. Above Barrel's refractive index of 1.58, where windowing ceases to be a significant problem, Harding's charts reveal that, like diamond, historically optimal cuts for other gems also sit just outside the dark zone. The best cuts do not avoid the observer's silhouette, they are using it for the contrast it creates. The role of observer obstruction and contrast in gem light performance. The goal is to make best use of available contrast in illumination. We can verify this by reverse ray tracing. Reverse ray tracing, by following a beam's path into the gem from the viewer's overhead position, generates what is called the gem's spectral reflection pattern, or SRP. The gem faceting community calls this the gem's light reflection pattern, or LRP. The spectral reflection pattern reveals how the ideal cut is designed and functions. It maps where the reflected light exiting toward the observer from each facet actually originated. For an ideal cut, this pattern shows the 16 key reflection points from the pavilion mains arranged in a configuration that sits just outside the 10-degree divergence circle, immediately beyond the boundary line, just as Harding's charts revealed. In other words, the main facets of the ideal cut are engineered to dance on the edge of darkness. This forces a re-evaluation of what observer obstruction means for gem beauty. The best cuts are not merely dodging the observer's head obstruction, they are leveraging it. They take advantage of the contrast available in lighting environments under which gems are typically viewed, especially the contrast created by bright overhead lighting against the relatively dark silhouette of the observer's head. That edge between bright light and darkness is the sweet spot. It is the dynamic zone where contrast is always present. Fundamentally, brilliance, fire, and scintillation all depend on illumination contrast. Remove the contrast and the ideal looks dead, lifeless, almost milky. The geometry is perfect. The light return is technically high, but there's no contrast. So, no sparkle, no fire. When the ideal is placed under high contrast spotlighting and observer head obstruction is introduced, the transformation is immediate. Vibrant flashes, spectral colors, and intense sparkle erupt. The difference is entirely due to lighting contrast taken best advantage of by the ideal cut. With movement, the 16 reflection points, those just outside the 10 degrees boundary, are swept back and forth across the contrast edge between the observer's head and the bright surrounding light. As a result, reflections rapidly blink on and off. This movement in and out of the high contrast zone creates scintillation, that dazzling sparkle that the eye sees. As reflections transition between bright and dark, flashes of colorful fire appear. This is fire enabled by contrast in illumination. It broadens our understanding of fire. Fire requires dispersion. Yes, the gem's ability to split white light into colors like a prism. That's physics inherent to the material. But illumination contrast must be present to enable it. Optical physics says dispersion is greatest when light enters or leaves at a greater angle to a facet. But if that reflection point from where the color should appear is just reflecting uniform brightness, the fire is missing. Fire requires illumination contrast. Taken together, the ideal cut is not merely a geometry designed to trap light and avoid windowing. It is a sophisticated optical design that accurately positions the 16 key pavilion main reflections into the dynamic high contrast zone created by the observer's head and surrounding diffuse and spotlighting. The dazzling light observed is literally dancing from the edge of the viewer's own silhouette and the nearby high contrast edges of spotlighting. That's the secret to maximizing the gem's potential brilliance, fire, and scintillation. It is remarkable to consider that decades of cutters, working through trial and error in pursuit of beauty, unknowingly perfected a design for diamond and each gem material that exploits this complex optical principle involving illumination contrast. The light performance of the benchmark of beauty, the ideal cut diamond, is fundamentally centered around and its beauty enhanced by the physical presence of the person admiring it.